All right, class, let's finish. I actually already wrote some things. I forgot to press start earlier. So let's finish graphing the trigonometric function. So the last two are the tangent and cotangent. So what I wrote here for you was that tangent is equal to sine over cosine, right? Just to remind you. So as you see, the tangent itself is a rational function. So if we've learned anything from the secant and cosecant, which we just graphed in the last video, is that this tangent function will not exist, right, whenever the denominator is equal to 0. So in other words, anytime cosine is equal to 0, tangent will be undefined, okay? So when is cosine equal to 0? Well, again, if we've learned anything from the secant and the cosecant, it's the same values where secant was undefined, because secant is 1 over cosine. So cosine is in fact equal to 0 up and down the y-axis, right? The pi over 2, 3 pi over 2, and so on and so on. So if you remember, how do we write an odd multiple of pi over 2? Again, it's undefined at 1 pi over 2, 3 pi over 2, 5 pi over 2. So any odd number, again, we can write it as 2k plus 1. That's going to turn into an odd pi over 2, right? So any odd multiple of pi over 2 has to be excluded from the domain. The range of the tangent function is in fact all real numbers. So this k is any integer. You have to write that, or else I wouldn't know what the heck k is. Okay, so I'm going to draw the tangent function for you. I'm going to tell you why the range is any integer. So what did I say? Anywhere where there's a pi over 2, I'm going to have to draw a vertical asymptote. Okay, and so on and so on. So let me draw it. At negative pi over 2, the function's undefined. At 1 pi over 2, at 3 pi over 2, at 5 pi over 2, at negative 3 pi over 2. This tangent's undefined. What does it do in between? By the way, tangent of 0, sine of 0 is 0 divided by cosine of 0 is 1. So 0 divided by 1 is 0. And then it grows up infinitely large. At pi, it's going to be 0, grows up infinitely large. So the thing is, and you can take your calculator and test it. This one should come in a little bit more evened out, not so linear. Yeah. Okay. So the thing is, this is a number less than 1. This is a number less than 1. You can take a quarter and divide it by 1/2, and you're going to get a half. You can take a half and divide it by a quarter, and you're going to get 2. You can take a super 0.9 divided by 0.01, and you're going to get 90. Okay, so you can divide numbers less than 1 and get yourself infinitely large numbers. So again, think about 0.99999 divided by 0.00001. Both are numbers less than 1, and when you divide them, you're going to get 9 gazillion, right? And so on and so on. So the range of these tangent is all real numbers. So as you see, the tangent also has a period. Very important fact. What's the period of the tangent, though? It looks to me like this matches this matches this. So if you think about how long it takes to go from here to here, or from here to here, you will easily see that the period of the tangent is only pi, not 2 pi. This would be 2 pi's. That's already 2 loops. So it's true. If you also think about your circle, yes, what happens with the tangent? Tangent's positive in the first quadrant, then negative, then what? Back to positive. So the tangent really repeats every pi. Whatever value you get here, it's going to be the same thing here, right? Take the sine and the cosine value, divide them. Take the sine and the cosine value, divide them. These are two positives. These are two negatives. They're going to get you the same answer. So the period of tangent is only pi. Now, if I were to choose one pretty loop of it, it would be this one. Many textbooks pick this and this just to stay on the positive side. It's up to you, right? Just the same as we broke secant, by the way, just to keep it on top of that cosine. It was a little broken up, so it's the same. Many textbooks make this one complete cycle of the tangent, which is true. I like this one here. It's up to you as long as it's one complete cycle, okay? All right, we'll have an easier time with cotangent. Cotangent is cosine over sine, so the domain of it is going to be exclude any values where the sine is equal to 0. When is sine equal to 0? Right, where y is 0 on the x-axis, right? So I'm going to have a unit circle right here. So the sine is 0, 0, pi, 2 pi, 3 pi, 4 pi, right? So any multiple of pi has to be excluded, yes, out of all real numbers, where k is any integer. And then the range, just as I said, will be all real numbers. So let's draw a cotangent function. So what I'm going to have to do at pi, 2 pi, 3 pi, and so on, negative pi, negative 2 pi, any multiple of pi, I have to draw myself, 0 pi included, 1 pi, and so on and so on. I have to draw myself a vertical asymptote. Halfway through, at pi over 2, by the way, cosine of pi over 2 is 1. 0, sine of pi over 2 is 1. And the cotangent, in fact, goes down. You don't need to make it, so that's pi over 2. That's 3 pi over 2. You don't need to make it weave in just like a cubic function. Remember, a cubic function really turns almost horizontal. They don't quite, but also don't make it very linear either. So don't draw a line. Try and make it curvy and change the, we call this concavity. And the graph turns the other way. Okay, so again, this is a little too linear for my taste. There you go. Okay, so that's what the graph of cotangent looks like. And if anything, remember how cotangent's the reciprocal of tangent, right? So whenever tangent is 0, the reciprocal of 0 is undefined, right? So I have a vertical tangent line anywhere where the tangent was equal to 0. Yes, so they're reciprocals of each other. When one gets higher, the other one gets lower. So that's why the fact that the graph is going to come down instead of going up. They're reciprocals, right? So the larger number you're dividing by, the smaller the answer gets. So same thing. This one's nice. What would be one nice loop of the cotangent function? It's this one from 0 to pi. Okay, so that would be one complete cycle from 0 to pi, and as you see, very well the same way, right? The period of cotangent is also pi, just like its reciprocal. Okay. All right, so let's just graph some tangents and cotangents. Think about the period. Think about where you might be shifting this. So this is what I would do. Sure enough, I could factor out the 1/2. I don't really think it matters. What I need to think about is where am I going to shift this and what is going to be this period. So definitely, what do we have? Because of this 1/2, the period is going to change. Yes. So why? the period before was a pi, right? For the tangent, the period is pi. I'm going to divide this by 1/2, and now I'm going to get a full 2 pi period for this, okay? Then what else am I going to do? I'm going to shift this whole thing to the right 2 pi units. Okay, so this is one thing I could do, 2 pi, and then the period of it will be 2 pi, so in other words, it's going to get to 4 pi, okay? So if you think about what the regular tangent looked like, so for me, this is what I like a tangent to look like, right? From negative pi over 2 to positive pi over 2. What happened to this? This thing got shifted to the right, to the right, pi over 2 units, and the period is 4 pi, but again, my beginning and my ends, I like them this way and that way. Okay. So there's my tangent function. Now, because again, the way I like to draw the tangents are not from 0 on, but centered at 0, half and half, okay? So, let me show you a super easy way to figure this out best. And it's the same way I've been showing you over and over again to try with the sine and the cosines if you are confused. So what am I going to do? I'm going to take my 1/2 x minus pi and put it in between where a tangent normally likes to live. And as I said, I like to draw this cycle, right? Instead of broken up, you can break it up half and half, but then, and you can go from 0 to pi, but I like to do the whole full thing, and again, textbooks vary on that. So I like to draw my tangent between negative pi over 2 and positive pi over 2. Okay, so negative pi over 2 and positive pi over 2. And by the way, I'm not saying or equal, because really what do I have at those two values? I have vertical asymptotes, right? So they're not really going to equal to that. They're staying in between. And then I'm going to take this and solve it for x. So what do I do to solve for x? I'm going to add pi. Okay. So negative 1/2 plus 1 is positive 1/2. And 1 plus 1/2 of these pi's is 3/2, or 1 1/2. Okay. And the last thing to do to get to x is multiply by 2. So then x will be drawn between pi and 3 pi. So is this what we drew? Exactly. Between pi and 3 pi, I made myself the two vertical asymptotes, and then I just drew the tangent in between. That's it. Okay. So what am I going to do with a 3 cotangent plus 2? Ooh. So I'm not really messing with the period of it. Nothing's multiplied to cotangent. So I'm going to make this a little bit even easier for you. So there's no phase shift, right? Nothing's multiplied. These are just vertical shifts. I have a vertical stretch by a factor of 3 and then move the graph 2 units up. So let me draw a regular cotangent for you. So a regular cotangent goes from 0 to pi, yes? That's what we just drew. This is where our vertical asymptotes are. So what does the cotangent look like? It's going to come down, turn, and come back down this way. Now, what is the 3 value going to do with this? The 3 will simply stretch vertically this graph by a factor of 3. So in other words, this value here is going to get 3 times larger. The 0 stays at 0. This value here will get 3 times larger. So the graph will be, well, super stretchy. By the way, one thing you can hold on to is this. What is tangent or cotangent at halfway between 0 and pi over 2 is pi over 4. So what happens at pi over 4 with tangent and cotangent? They're equal to 1, okay? So that's one value you can hold on to if you should have to have a stretch. So this one value goes up to 3. This -1 value goes down to -3. Just make it stretchy. And then what else is going to happen to this? The +2 does what? Shifts the graph 2 units up. Okay. All right, I don't have any other colors. So that means what? This point is going to go here. This is the most important one, right? This turning point is going to be, I'll make it black, 2 units up. So it's coming super stretchy, but it's still turning down here. So yeah, it looks almost linear, but it's not. So this is my function right here. Okay, so just simply what moved 2 units up, which is also why maybe you would want to make, in this case, these units much, much smaller, right? So that you don't have to stretch it quite so large, okay, or move it up so much. But yeah, okay. So again, using a lot of the transformations in our graphs. So I have 2 more, just need a little bit more practice. We didn't need quite as much practice with secants and cosecants because we got plenty practice for sines and cosines, and that's all your graphing. So let's see about this. What am I going to do with this graph? So it's a cotangent that got multiplied by a factor, right, of 2. If you think about this, again, going from 0 to pi and shifting it pi over 6 units left, and then cutting your period, it just, it gets too confusing. So, especially for tangent and cotangent, which kind of vary, this is really, really what I recommend you do. So you might get away with sines and cosines on where the starting point is and where the end point is because of the amplitude and period and phase shift and all that. But I think for tangent and cotangent, they get a little too crazy. So where do we like to just solve the double inequality? Where do we like to draw a cotangent in between? Well, we just saw it from 0 to, this is a cotangent function. Draw it for yourself again if you want. From 0 to, right? From 0 to pi, that's a regular cotangent. Okay, so I'm taking this argument that's inside the cotangent and putting it between 0 and pi and solving this. So the first thing I'm going to do is minus pi over 2. And from 1, when you take a half away, you're just left with half. And then what else do I do? Divide by 3. So same thing as I did with another example, because you don't want to write over 3 as well, since these are fractions already. I'm just going to multiply by 1/3. So then that gets you negative pi over 6. And positive pi over 6, I said no equal. Perfect, easily done. Okay, so now I know, done. I don't even need to worry about a thing. I'm going to draw myself one complete cycle between negative pi over 6 and positive pi over 6. What could be prettier? Right there. This is where my 2 vertical asymptotes are. Halfway through, the cotangent gets down to 0, okay? And what's the other thing that we haven't taken care of? I haven't taken care of this, so I have to show a stretch, a vertical stretch. Boom, that's my vertical stretch. Halfway through, as I said, we get to 1 with a regular tangent and cotangent. So fine. halfway through, I get to 2. You get to pick, right? You get to draw and pick your units. Make them as wide as you want, as small as you want. Labeling is everything. This could look like any regular cotangent function, except for I shifted, yes, my axis. I labeled the points instead of 0 to pi. I put negative pi over 6 to positive pi over 6, yes. Shifted my axis, and it looks just like any other cotangent function. Okay, so here it is, one more. And just to make it even more challenging, I'm just going to throw another minus pi. It could have been super easy without. But here it is. What am I going to do with this? Where do we like to draw a tangent in between? We like to draw a tangent in between negative pi over 2 to a positive pi over 2. Yes, that's how we drew our tangent earlier. From negative pi over 2 to the positive pi over 2. That's a regular tangent function, right? And then it goes up and down, boom, like a cubic function. So that's a regular tangent, okay? So then I'm going to take whatever's inside this tangent and put it between those two values and solve for x. So what do? Add the 1 pi. And again, all you're doing is really adding fractions. Ignore the pi. Negative 1/2 plus 1 is positive 1/2. 1/2 plus 1, right? So 1/2 plus 1 is 3/2 of these pi's. And then again, divide by 2, so multiply by 1/2, right? Again, it doesn't look good to have 3/2 over 2. It looks like, ooh, what is that? Well, to divide by 2 is the same thing as multiplying by 1/2. So I'm going to draw this thing between 1/4 pi and 1/3 pi over 4, okay? So this is 1 pi over 4, or right, 1/4 pi or pi over 4, 2, 1, 2, 3 pi over 4. And by the way, halfway through is 2 pi over 4, which of course is pi over 2. What happens at the ends? This is where I have my vertical asymptotes. Okay, I could have made it wider a little bit just to see better. Okay, so that's my vertical asymptotes. That's what a tangent looks like, except for what's happening this time. It got stretched and flipped. So instead of going up, I'm going to make it come down. And how do I show that it's also been multiplied by 3? Halfway through this point here, that's a 3. Halfway through this point here, that's a negative 3. So again, that accounts for that pi over 4, right? Stretchy, so a pi over 4 normally, right? This is what tangent of pi over 4 is. It's 1. What's tangent of negative pi over 4? It's a negative 1, okay? So that's the only point, because when you stretch 0, you still have a 0, so you can't do that. So that's the only point where you could show a vertical stretch, right? So 1/4 of the way through, yes, I'm already up at 3, right? Or at negative 3. Okay, so this is graphing tangent functions. Of course, if we should need to draw more, what do? I just copy and paste this graph over and over again. What's the period of this one, by the way, is pi over 2, right? So the period of tangent is pi. This one's pi over 2. I'm just going to write this one here. The period is pi over 3. So from negative pi over 6 to positive pi over 6 is a pi over 3. It's 2 pi over 6, which is pi over 3, right? It's just adding fractions. Same thing here. So I'm going a pi half over. So pi over 2, here I'll take, this is what I'm doing in my head. So from 3 pi over 4 to add another pi over 2 period, yes? I need a common denominator, so that's 5 pi over 4. So that's the next guy here. Okay, so I'm going up by 2's. There you go. And then I can draw another one at 7 pi over 4, right? So it just keeps on going. And then minus 1 pi over 2, and you'll get, by the way, to negative pi over 4. That's your next vertical tangent line, and that's your next graph coming down. There you go. That's it. Okay. So that's in case you don't just have to draw one, but multiple, all of it, right? Just keeps getting copied over and over. So without labeling, there is no credit. That's the most important part. Label your axes, or else it looks like anything else, so I might as well not ask you, right? So I know many of you will just put this in your graphing calculator, and I just see this for answers. Just like, what the heck is this? Nothing. Means nothing. Where does it cross? What is this? You just, I know you see this stuff on your graphing calculator. A bunch of waves, great, means nothing to me, okay? So, labeling, right? That's important. And that's how we come up with the answers. Again, I figured all these problems, right? And just make them up, figure them all out alongside with you as we go. So that's the important part. Figuring things out for yourself. Remember, you're going to calculus from here, so there you go.